Newton's third law. For every action, there is an equal and opposite reaction.
Kyle Adams doubts the reality of Newton's third law of motion, action-reaction. Kyle tried this little experiment. Stand facing a wall, your feet maybe 16, 18 inches away from the wall, and then lean forward like this with your face just above the wall. Pull your hands away quickly and try to right yourself. Can't be done. However, if you push against the wall even gently, you right up like that. It's because I push against the wall and the wall pushes back against me. That, my friend, is Newton's third law of motion.
That is something I directly addressed at the end of my Newton's failure video. If you actually finished the video he was responding to, he would have heard Professor Dave Explains say the same thing and heard my rebuttal to that.
Think of a car hitting a brick wall. The car imparts an action force on the wall from its motion, and the wall imparts a reaction force right back on the car, bringing it to a quick stop. These vectors are equal in length and point in opposite directions.
Really, Dave? You claim that wall is pushing on the car with an equal amount of force? Though that car is pushing on the wall, that wall is not pushing back. The molecular bonds of that wall are just simply strong enough not to break. If they were weaker, the car would go right through the wall. If I were to have one car come and crash into an identical car traveling at the exact same speed in a head-on collision, that would be considered an equal amount of force. Herein, you should agree with me that that would be different than one car hitting a stationary wall.
This is illustrated by the following expression, where m1v1 plus m2v2 is equal to the sum of the masses times v final, which will depend on the magnitudes and directions of the two initial velocities. This approach can also be used to model car collisions, whether the two cars were moving in the same direction or opposite directions. Adding the masses of the cars and combining the velocity vectors will tell us what will happen after the collision.
Please tell me that you agree with me that the mass and velocity of a car plus the identical mass and velocity of another car is not going to be the same as the mass and velocity of a car plus the mass and velocity of a stationary wall. According to an auto accident attorney, head-on collisions are the most dangerous because the force of the impact is doubled due to the speed of each vehicle. Therefore, even a relatively slow auto accident with each car traveling just at 25 miles an hour will result in a tremendous impact, equal to the force of hitting a wall at 50 miles an hour. This is literally as simple as 1 plus 1 equals 2, and 1 plus 0 equals 1.
Just repeating what Dave said does not refute my point. Now let's talk about archery. Archery mechanics work because Newton's third law does not. To that, Ben on our debate board says,
Why? The force pair between arrow and drawstring are equal and opposite. The net force on the arrow is imbalanced, so the arrow accelerates.
Again, Newton's third law states for every action there is an equal and opposite reaction. Since the arrow in archery does not provide an equal and opposite force, archery depends on the breaking of Newton's third law.
Circled in blue is the free body diagram for the arrow. There is one force acting on it, indicated by the red arrow due to the force on the arrow from the string. The string experiences an equal and opposite force due to the arrow. Since there is only one imbalanced force acting on the arrow accelerates.
Since there is one imbalanced force acting on the arrow accelerates. I fully agree with that.
Sure, there's one force on the arrow, and the corresponding equal and opposite force is on the drawstring.
If there was an equal and opposite force on the drawstring, that would make it a balanced force, not an imbalanced force, and the drawstring wouldn't move. The movement of that arrow depends on the movement of that drawstring.
But the forces are not both acting on the same object. I'll refer to this diagram again. For the arrow to be experiencing balanced forces, both action and reaction force would have to be acting on only the arrow. But that isn't the case. The action is on the arrow, the reaction is on the drawstring.
The string is acting on the arrow, and if the arrow is providing an equal amount of force on that string, how would that not be balanced?
Again, look at the diagram. The blue circled part would be the free body diagram for the arrow. The arrow only experiences the force from the string, and the force is unbalanced.
Does that mean you believe every object is imbalanced? How is that different from you drawing a stationary box sitting on a table without drawing the table?
If the box is supposed to represent a box on a table, then you're missing gravity. I skipped it in the arrow example because it's perpendicular to the forces we were interested in.
Your diagram is showing the arrow after it's been shot then, not while it's resting on the string?
Sure, Otherwise the net force on the arrow would have to be 0. If you're still holding the drawstring, then the force of the drawstring on the arrow is 0.
With that being the case, your arrow in motion is off topic. My opening statement was about the force that causes the arrow to be put into motion, with the arrow still touching the drawstring. If Newton's third law was right, the drawstring and the arrow would be balanced, and then the arrow would not be able to move anywhere. But since the forces are not balanced, the drawstring overpowers the arrow and makes it so when the archer lets go, the arrow gets launched.
I thought your argument was that if Newton's third law applied, then the arrow wouldn't be able to move. I've shown that after the drawstring is released there is an equal and opposite force between arrow and drawstring, and a net force on the arrow that causes it to move. Before the drawstring is released, nothing is moving and the forces are all balanced.
What force do you claim is acting on the arrow in motion other than gravity?
Initially it experiences a force on it from the drawstring. The red arrow represents that.
Okay, so we're back to the arrow touching the string again. Great.
Do we agree that after the drawstring is released the arrow experiences an unbalanced force?
Yes, that is what I've been saying this whole time.
Do we agree that the drawstring experiences an equal and opposite force?
No! Have you not been listening to me? If it did, it wouldn't be moving anywhere. And now we're back to the beginning. Our conversation continues, but since we're back to the beginning, I'm going to call that the end of round 1. Our big takeaway from round 1 being our common ground, that the arrow accelerates due to an imbalance of forces. I feel like that totally agrees with my statement and utterly contradicts Newton's equal and opposite forces, but we'll talk more about that next time. Thank you all for watching. This message has been brought to you by the Flat Earth Institute of Science, with a special thank you to Benjamin James Muthig. It has been a pleasure to talk to you.
Hey Karen, being the current queen of Flat Earth, it must be hard to find Flat Earth friends. Do you know an easy way to find cool people like yourself and solid info about our stationary, horizontal level plane?
Why, yes, that would be the Flat Earth Sun, Moon, and Zodiac Clock app.
It's the perfect gift for friends, family, and complete strangers. Watch the featured video every day for 2 weeks and see what happens. It'll be the best $2.99 you've ever spent.